Okay, so we are, if you recall, on Wednesday we introduced the concept of equilibrium criteria, where we have to have the temperatures equal, which is thermal equilibrium, pressures equal, mechanical, and then lastly the Gibbs free energy has to be equal, and that would be chemical equilibrium. So when we get to a new concept like this here, I like to review everything, and the cool thing about thermodynamics is that if we skip over the details, we can basically go from the beginning of time to where we're at right now and remind ourselves of all the complexity that we had to jump over and skip over, right? And remind ourselves that most all of what we're learning about is sort of the arbitrariness of defining certain variables to make it easier on ourselves. So let's do an overall recap, and then we'll return to phase equilibrium once we refresh ourselves and remind us that what we're doing actually has a really solid basis in the fundamental laws. So first step, we had our first law. The first law of thermodynamics is only a way of restating the law of conservation of energy, where we have a change in internal energy. This is how matter stores energy. And recall that back in the 1800s and 1700s when we were developing thermodynamics, we didn't know about atomic theory, so we just were able to say, don't worry about it, the matter stores energy, right? It's just safe and sound. We can interact with the energy that's stored in matter by adding or subtracting heat or adding and subtracting work through either some expanding process or PV work going on in the system. Right, but the first law is just a restatement of the law of conservation of energy. Now we take this expression here and we typically expand it for our purposes as chemical engineers because we like to talk about processes. So we like to monitor how the total energy of a certain process changes with respect to time by including energy that flows in the form of enthalpy plus energy that forms in heat, shaft work, and minus PdV, which is the volume expansion work. We develop this longer expression by manipulating this more simple first law for a closed system. Next, we have the second law, where fundamentally, the second law can be defined as saying that the rate of entropy always increases for any real process. But equally as important in my mind is that it has to be a concave function, otherwise the universe is unstable. And then I'll also add in, I guess, a 2' here, and that's the Gibbs phase rule. It's not called the Gibbs phase rule quite yet, but same idea. And that effectively says that U, V, and S are the three primary fundamental variables of the universe. We could also say mass, right? Or we could write this as specific internal energy, specific volume, and specific entropy. So with these three concepts, that allows us to manipulate our thermodynamic relationships with respect to just fundamental calculus, right, where we expand on the rate of change in internal energy, for example, with respect to volume and entropy. But without knowing the limitation of how many variables can fully describe a system, we can't undertake this process. So we need to have the understanding that all of thermodynamics effectively just relates between these three fundamental variables. Everything else that we do from that point onwards is effectively made up. So what we did here, the next step was define additional variables. Now these are variables of convenience. They include temperature, pressure, right? Temperature and pressure are defined based on relationships between these three variables, where it is ds du is 1 over temperature, and du dv at constant s is equal to negative pressure. Hopefully I don't have those messed up. We also define the Gibbs free energy, the enthalpy, the Helmholtz energy, and so on and so forth. These are all defined variables, units of convenience. Enthalpy is useful when we're dealing with an open system, right? Because the fluid itself has to push itself into the system, and that includes a little bit of energy. When the system kicks some fluid out, that takes a little bit of extra energy. That includes this PV term. So what we talked about on Wednesday, next step here. So when we take the first and second law, plus some calculus, right? Now this is just the general calculus of the chain rule, where we expand, for example, if we take du expanded with respect to, let's say, so I'll give you an example. So if we expand u with respect to v and s, this is how we started everything off, we can write that the total rate of change in the internal energy is related to all of the partial changes, dv with constant s, dv plus s constant s. And this is how we were able to relate between general relationships in calculus, right? These are totally assumption-free mathematical relationships that are valid for any function you ever want to look at. We were able to relate this with a combined version of the first and second law. And from here, we were able to develop relationships for du with respect to t and v, were the most convenient units. Change in enthalpy with respect to temperature and pressure, the change in entropy with respect to temperature and pressure, or change in entropy with respect to temperature and volume. So I'm not going to write down all the relationships that we have, all those equation sheet handouts that have all these different relationships. So what these expressions allow us to do is they allow us to relate the variables that we can measure in the laboratory to the variables that we can't measure in the laboratory, internal energy, enthalpy, and entropy, making sure that we're not violating any of the previous relationships that we've done. So anytime you see any of these expressions for du, dh, ds, ds, and whatever the case is, remind yourself, all that is a restatement of the first and second laws of thermodynamics. There's nothing else more complex than that. And the only assumptions that we make to get to this point right here is that, one, we're dealing with a reversible system, and that's basically it, right? And this, if we write it as specific, right, with the underbar, then that also means that we're kind of assuming it's a closed system. But these are 100% assumption-free derivations and processes. Then what we talked about on Wednesday was that the change of entropy is equal to 0 at equilibrium. 0 at equilibrium. And by working with entropy and energy balances, we were able to show that at equilibrium, the temperature of phase 1 has to be equal to the temperature of phase 2. That is our thermal equilibrium criteria. The pressure of phase 1 has to be equal to the pressure of phase 2. This is our mechanical equilibrium. And then lastly, the Gibbs free energy of phase 1 has to be equal to the Gibbs free energy of phase 2, and this is our chemical equilibrium. This last one is by far obviously the hardest one to deal with. The last thing that we did that was going to become relevant is based on the stability criteria that entropy has to be a concave function. We were able to demonstrate that the heat capacities always have to be greater than 0, and the more specifically relevant one for today's discussion is that the change in pressure with respect to volume at a constant temperature always has to be negative, less than 0. This is what we're going to be exploiting today to talk about phase changes. So the key thing to keep in mind, every time you see a complex and tedious looking equation in thermodynamics, remind yourself that all it is a restatement of these two relationships. And then we have manipulated it based on variables that we have defined and noting that we only have a certain number of variables that we have to expand our properties and systems to. So all the weird, funky equations that we see are just a restatement of the first and second laws of thermodynamics. Okay, so that's basically recapping the first 3 weeks of class in, I don't know, 5 minutes, 10 minutes, about? Okay. So moving on to the new content. So we talked about on last class this criteria here, how we can know when two systems are in equilibrium. Now what we're going to talk about specifically is, in this case we call system 1 and system 2, we're going to be referring to this as phase 1 and phase 2. The simplest and most common phase equilibrium that we're going to deal with as chemical engineers is going to be vapor-liquid phase equilibrium, and that's what we're going to be focusing our discussion on. This criteria right here, that that pressure and volume always have to have an inverse relationship, is going to be the key that we're going to use to exploit that. So for today's content, I'll call it phase equilibrium from an equation of state. Equation of state. So the simplest equation of state that we all know about is the ideal gas law. We talked about this a little bit on Wednesday. The ideal gas law is great for a lot of circumstances, low pressures, high temperatures. And if we take this partial derivative, where we rearrange this, pressure is equal to RT over V. We take the derivative, and it is equal to minus RT over squared. So the ideal gas law is always stable. But the problem is, the ideal gas law is kind of useless. Because according to the ideal gas law, if every material in the universe behaved according to the ideal gas law, we could not have solids, we could not have liquids, we could only have gases that don't interact with one another. So in terms of using an equation of state to solve for changes in internal energy, enthalpy, and specifically changes in phase, it's an absolutely useless expression. We need to have something that's more advanced and more elaborate. So the next step up of equations of state and complexity, anyone know how to venture a guess? What's the next step up in complexity that most people will learn about in terms of equations of state? Before the van der Waals. So we have ideal gas. What's one step up in difficulty from the ideal gas? Was that what you say?
Real gas.
So real gas. So all the other ones, the goal is to model a real gas. I know you guys have heard of this one. So it's not a van der Waals. Van der Waals is a cubic equation of state. We're actually going to talk about one that's actually a quadratic equation of state. But you don't refer to it typically like that. Virial. Who's heard of the virial? A few people have heard of the virial. Okay. So the virial equation of state. Virial equation of state has a very strong theoretical basis in statistical mechanics. We oftentimes write it as pressure volume over RT. We define this as something called the compressibility factor, Z. Is this starting to ring a bell? Good. And that is, this B of T term is called the second virial coefficient. And you can calculate it by knowledge of how attractive or repulsive particles are. So when you actually think about matter as being composed of atoms that have attraction and repulsion, this is the formula and equation of state that you actually can end up developing after a lot of approximations and assumptions. So we'll talk about where this equation actually comes from later on in the class when we talk about statistical mechanics. But if we take this expression and we rearrange it, right, for now, and our purposes in classical thermo, we're going to view equations of state as kind of just like tools, useful features that we can use to help us solve problems. So if we rearrange this expression, and we do some cross multiplying and some fancy, actually relatively straightforward mathematics. right, we can demonstrate that this is effectively a quadratic function. So if we were to look at, excuse me, the Virial equation of state on a pressure versus volume diagram, it should look like a parabola. But how should I draw it? Should I draw it convex or should I draw it concave? How can I know?
Convex. That depends on temperature problem.
Stability criteria.
Well, so in terms of stability criteria, there's actually going to be two scenarios, right? So this is a quadratic function, so it's going to have a region of positive slope and a region of negative slope, right? But should I draw it as a smiling up function or a frowning down function? Which of the two, and how do I know? So I'm doing pressure versus volume. Yeah.
No.
So how do I know from just general calculus? Think back to high school.
First coefficient.
Yeah,
For me.
that can never be negative because it's pressure.
It's always positive.
But let's just think fundamentally. What should I calculate to know?
Double derivative.
Double derivative of what with respect to what?
Double derivative of V with respect, double derivative of the equation with respect to V.
Pressure with respect to volume. So in the case when I have to remind myself and go back all of my days of calculus, I'm like, okay, y and x, dy squared, dx squared. That's what I need to calculate. So let's do that very, very quickly. So the second derivative of pressure with respect to the internal volume holding temperature constant, which is this is one of our stability criteria, but it's also effectively what we're trying to draw here, right? The reason why I have pressure, volume, and then holding temperature constant is, remember, an equation of state is relating pressure, temperature, and specific volume, right? So if I'm taking the derivative of if two of the variables are drawn in the derivative, everything else has to be constant. So this is just going to be equal to, this is the 2, then that goes away, so it'd be 2p over RT. Pressure is always positive, temperature is always positive, R is obviously a positive number, which means this is going to be a convex function, so it'll look something like this. Okay. So, if I'm using the Virial equation of state, and let's say, for example, I know the system pressure. I'm going to say this is my system pressure here. I want to know what is the density of my fluid at this temperature, right? Because this is an isotherm. Temperature equals constant. We call this an isotherm. I want to know what is my density. Oh, here's a problem. Right, and if you recall, we're going to go back to the Algebra 2 days. Right, when you want to solve a function, you can do it graphically just by drawing two lines. This solid line, this is the curve of this function here. I'm holding pressure constant, which is the dashed line. So the solution to the equation of holding pressure constant and following the Virial equation of state, there are two solutions. Which of these two is the correct solution?
Left one.
Why?
Stability criteria.
Exactly. So from this region onwards, we have a negative slope, which means we have a stable fluid. From this section onwards here, we have a unstable fluid. Now we got to remind ourselves why this is the case. This all comes back to entropy. So if we look at a plot of entropy with respect to any variable in the system, for this case, let's just say it's volume. It has to look like this. It has to be concave. Now if we were doing the opposite, if we said entropy were convex, and had a shape that looked like this. Now, fluids are always in sort of slightly fluctuations and very slight motions, right? equilibrium as we discuss it is a dynamic equilibrium in thermodynamics. So if I have a glass of water, all right, and I trap some air and I put a cover over it, eventually that water is going to be in equilibrium with the air. That doesn't mean that all the water molecules that are vapor are going to stay vapor for all time. No, they're going to exchange. Some are going to hop in the liquid and some liquid molecules are going to pop up again. Right? So this is always in a dynamic process. So even in a fluid, like an ideal gas, this density is the average density or the average specific volume. You're going to have slight statistical variations, right? And this all makes sense a little bit because everything's a little fluctuating and moving around. So in the case of an unstable fluid, what that means is you're going to have very slight variations from the mean specific volume, let's say. And then, in fact, let me draw this a little bit differently so you can actually line them all up. Okay. So if we have an average volume, I'll call it the mean volume, specific volume here, and I have my two curves of my entropy shape, and they intersect at that same point. One of them is convex and one of them is concave. Right? Equilibrium is reached effectively when we're at maximum entropy. So in the concave function, if I have slight statistical variations in the system, that lowers the entropy. Right? That's the definition of a concave function. It's the easiest to see when you draw it at a maximum. Right? So if you split this into two slightly different microdomains, you can see that adding these two up and dividing by 2 is less than this one here. For a convex function, if you split into two small phase domains, you're increasing the entropy. So if I look at the entropy with respect to changes in in specific volume, for the concave function, any slight statistical variation in the density of the fluid will actually lower the entropy and the system will want to snap back to the mean. Conversely, if I have the system with a convex function of entropy, any slight variation in the density will increase the entropy, and then it'll continue to grow and grow and grow and grow. And that's what we mean by having an unstable fluid. So in the example that we gave last class with like superheating your liquid, right? That's why we have boiling chips in chemistry. If you superheat your liquid, right, any slight perturbation, right, is going to cause that thing to start to boil. So that's when you put like a little, I don't know if you have really clean cookware, but if you're boiling water for pasta and you put some salt in, sometimes it'll boil up violently. That's because you superheated your water. So you can superheat until the point where you get to an unstable fluid. And that's what we're going to be talking about next with the cubic equation of state. Any questions? So the virial equation of state, you can actually figure out which of these two roots is the valid one. And it's sometimes a bit tricky because then you have to basically take the second derivative and realize where you're at, or the first derivative and make sure you've got the root that has a positive first derivative. Yes?
How can we reach unstable fluid?
So how can we create an unstable fluid? So the most common way to create an unstable fluid, we're getting a little ahead, but we can create a phase diagram. And liquid-liquid equilibrium is really the most straightforward way to do it. With superheating, you can superheat like a pot of boiling water, and you can keep on putting energy, keep on putting energy, keep on putting energy. But at some point, right, we had the two lines. The binodal line, that's the line where the two phases want to phase separate, and that's their equilibrium compositions. But we also defined a spinodal line, which is the region of phase instability. So if we were to, let's say, look at a PV diagram again, and we were to draw these two lines out, this is our critical point, this is our liquid phase, this is our vapor phase, and we have lines that kind of go across and look like this. We have an additional region here called the spinodal region. So when we're superheating a liquid, we're basically going into this region right here. Right? The fluid wants to be on the binodal. These are the two phase coexistence points. So this would be the saturated liquid, this would be the saturated vapor. But we can subcool the vapor or superheat the liquid up until the point where we hit the spinodal, and then everything catastrophically falls apart. So another way, you can also think of this too, and this is getting into liquid-liquid equilibrium a little bit, but if you have a polymer solution in water, or a polymer solution in a solvent, it'll also have a phase equilibrium. where at some point when you cool the system down, or even some polymers when you heat the system up, it'll want to phase separate into a solvent-rich phase and a polymer-rich phase. So oftentimes, if you want a particular structure, you can have your solution up here at a high temperature where it's soluble, and then quench the temperature really quickly into the spinodal region. And precipitating out in the spinodal and precipitating out in the binodal actually have two different mechanisms. And so you can create different patterns if you're making devices by subcooling it into the spinodal region or the binodal region. But the short answer to your question is you just got to keep going. So you can't superheat or subcool forever. Eventually, it'll turn unstable. And when it turns unstable, then entropy always increases when you modify it a little bit. Okay. Now on to the main event. So we've covered the relatively useless ideal gas law, the slightly more useful virial equation of state. Virial equation of state is really only useful when you're far away from a phase transition. When you get close to a phase transition, that's when it kind of falls apart, because the properties fluctuate quite significantly when you get near the critical point or when you get near a phase transition. But far away from it, virial is a significant improvement on the ideal gas law. But it's not so much simpler that you're better off you might as well just use a cubic equation of state that's significantly more accurate. So the virial kind of falls in this middle ground where it's kind of useful. We like to teach it in thermodynamics because it has a really strong theoretical basis, whereas cubic equations of state, they match the properties of real systems very well, but their basis should be best viewed as sort of semi-empirical. Okay, cubic equation of state. Cubic equation of state. So the simplest one, is which? We have heard of it many times. Van der Waals equation. Van der Waals equation is terribly inaccurate, but it's a great example. Most cubic equations of state are written as pressure explicit equations, meaning they're solved for pressure, and then the implicit variable. Okay. So RT over V minus B minus A over B. This is our format for the cubic equation of state. So let's test everyone's memory. What does this coefficient B represent?
Volume of the molecules?
Volume of the molecules or the excluded volume? Meaning that as my density gets very low, this B term is a really small number. But in an ideal gas, I can compress my fluid to a volume of 0, right? Or to the volume of one single molecule, because according to the ideal gas law, there are no other molecules in the system. It is literally just one, and then every one is a collective, additive effect of all that single ones. What does A represent?
Interaction parameter.
It's interaction. The interaction parameter becomes more significant, right, when the density gets smaller. Right? This term grows quite a bit higher the smaller this number gets. So this term is insignificant when the specific volume is very, very low, or in the case of a PV curve, right, when you get to really high specific volumes, right, for like the ideal gas law, it'll just keep on going forever and ever and ever and ever and ever and ever. Right, so in these regions over here, you have a specific volume. Right, is that right? Specific volume that is, oh, sorry, yeah, very, very large. So when you have it in the denominator, it's a very insignificant effect. Okay, so question time. A is greater than 0 or A is less than 0. Pressure goes up or pressure goes down. Okay, so if A is if A is greater than 0, how does my pressure behave?
Pressure goes down.
Pressure goes
Down.
down. If A is less than 0, the pressure goes up. Which of these two scenarios represents molecules that want to be near each other, or it's an attractive interaction?
Greater than 0?
Greater than 0.
Why? right? So if they're attracted to one another, they're not attracted to the walls. So this is a attractive, and this is repulsive. Which of these scenarios do we think is the most common of the two? Attractive. Molecules in general are attracted to one another, except in the case of when they get very, very close together, then they are repulsive. Right, van der Waals attraction, there is no fundamental theoretical repulsion in a molecular picture of an atom. They all want to be close together, except when you get to the point where they're so densely packed that the electron clouds start to overlap and you have electrostatic repulsion. But in general, molecules are always attracted to one another. Now, the reasoning behind that is, let's say we have a simple hydrocarbon compound versus, let's say, a different hydrocarbon compound. Let's say 1, 2, 3, 4, 5, let's say 6 and 6. So we have hexane, hexane, and then a cyclohexane. How van der Waals attraction works is that the electrons in a hydrocarbon, they're not particularly mobile, but they're still a little bit mobile. So what will end up happening is the electrons will slosh around a little bit on average. Oops, sorry, that's not what I did. And the electrons will slosh around just a little bit on average. And the way that the electrons slosh around is going to be dependent on the bonding structure of your molecule. What type of atoms? Is it hydrocarbons? Is there oxygen? Is there nitrogen? Is there sulfur? But the frequency at which these atoms slosh around is going to be defined by the molecular properties. The only other material that is going to have exactly the same characteristics is itself. So when these molecules slosh around, you're going to have slightly positive and slightly negative, and slightly negative and slightly positive regions. So that means these two are always going to want to be attracted to one another. Now, in the case of a different bonding structure, maybe you do still have electrostatic sloshing around a little bit, but it's never going to be quite the same. It's always going to be a little bit different. So these two compounds, they still might like each other. Their frequencies might mesh up pretty well. But it's never going to be the same as if you have two of the exact same compounds. So in general, identical molecules are always going to be attractive. Dissimilar molecules may or may not be attractive, and those interactions are non-trivial to predict. But that's why for any real system, the most general default is going to be that molecules want to be attractive to one another, and that your A parameter is going to be greater than 0. Okay, let's see. I'm getting a little bit long-winded. So if we rearrange the cubic equation of state, we can indicate or demonstrate why we call it a cubic equation of state. So for the van der Waals equation, I'm going to skip the arithmetic and go straight to the conclusions. But we can rewrite it literally as a cubic function. Right, where we can think of this as coefficient A, this is coefficient B, this is coefficient C, and this is coefficient D, with V as our variable. So a lot of literature resources will have a big table with a dozen different cubic equations of state. And all that they report is A, B, C, and D. As a nice compact way to communicate how to solve your variables. The reasoning behind that then is a lot of what we do in thermodynamics can be algorithmic. So if we had one cubic equation of state solver, if we wanted to modify it from, let's say, the van der Waals equation to the Peng-Robinson equation, all we have to do is recalculate A, B, C, D coefficients, and we can use exactly the same code that we already have in existence. Right? Again, that's why I always stress that we're teaching the system of thermodynamics, not necessarily sort of the answer to all problems. We're just teaching you what is the best way that we've come up with so far to try and solve these problems. Okay. So I'm going to draw this very large, and we're going to spend a lot of time talking about this drawing here. So I would recommend drawing it large on your notes as well. going to draw up the cubic equation of state here. And we're going to be highlighting a lot of its features, including how we can use it for phase transitions. So you will encounter this in your homework. You will be doing this exact solution process in your homework. And then the next assignment, you'll be doing it on steroids, basically. This is an isotherm, meaning the temperature is constant, or that dT is equal to 0. All different ways to think about it. When you plot out a cubic equation of state, you will be very frustrated because you'll think, oh, why aren't I getting this nice, beautiful functionality? Because this region is very, very small. Sometimes it's hard to find, right? Because we don't typically think about what this variable means, specific volume, but the specific volume of a gas is many times larger, orders of magnitude larger than the specific volume of a liquid, which means that you're going to have to plot this out probably on a log-log plot to even find this region. So it's going to be difficult to actually find it. Secondly, this might go negative, and that's okay. So this is a liquid over here. Over here is a vapor. From this point to this point, we're going to have an unstable fluid. And this is because the slope is positive. And then outside of these other regions, it's going to be negative, which is okay. That's our stability criteria. Now, the reason why the cubic equation of state is so useful is because it replicates the behavior of a real system. We have a continuous phase in the vapor that is stable. We have a continuous phase in the liquid, right? So the cubic equation of state can actually predict liquid density and liquid properties. And we have a discontinuity. We have a region that isolates those two phases. Right? So a first order phase transition, what we call this, a vapor-liquid phase transition, is a discontinuity. Right? There's a step change in enthalpy, heat of vaporization. There's a step change in entropy, entropy of vaporization. There's a step change in density. Those are all discontinuities, and the cubic equation of state represents those discontinuities. So according to our equilibrium criteria, temperature has to equal constant across the phase transition, pressure has to be equal constant, and the Gibbs free energy has to be constant. Okay? Temperature being constant, done, satisfied that, right? We're following along an isotherm. Pressure has to be equal constant. We can accomplish that, right? We just got to draw a horizontal line. And I'll just draw this particular one arbitrarily here. Okay, I'm going to label these 2 points. I'm going to label these ones, so I'll make sure I get my notes right here. This is, I'm going to call this pressure B, which is the maximum. I'm going to call this pressure A, and I'm going to call this one pressure alpha. Okay, I've arbitrarily drawn a pressure. Last step, how do I know the Gibbs free energy is a constant? And so let's take a look at our combined first and second law for Gibbs free energy. Remember, this is just a restatement of the first and second law. Our temperature is constant, so dT goes to 0. Delta G, which is equal to the Gibbs free energy of the vapor minus the Gibbs free energy of the liquid, transitioning from a liquid to a vapor, is going to be the integration of the Gibbs free energy going from a liquid to a vapor, which is going to be the integration going from a liquid to vapor of V dP. We're integrating the volume with respect to pressure. Now, this is a little bit different because typically we integrate with respect to the x-axis. In this case, we're integrating with respect to the y-axis, but the math works out all the same. Does anyone want to venture a guess as to what this P alpha represents? What's the real property? What's the meaning behind this P alpha? right? It's the pressure that satisfies the three equilibrium criteria. We also call that the vapor pressure. But I don't know where to draw this line. I have to choose where to draw this line so that I satisfy that my Gibbs free energy is constant. Only by satisfying all three of these equilibrium relationships simultaneously do I know that I have my system in equilibrium. And that means from an equation of state, I can calculate all of the different properties of the system, right? We haven't talked about it yet, but the change of the vapor pressure with respect to temperature is proportional to the heat of vaporization. This is what they know as the Clapeyron equation, where the simplified version is the Clausius-Clapeyron equation. So, with an equation of state, I can get access to vapor pressures. From vapor pressures, I can get access to heats of vaporization. By relating the heat of vaporization to the Gibbs free energy and the temperature, I can get the delta S of vaporization. So if I have access to only the heat capacity of an ideal gas, I integrate that to a phase transition following an equation of state, use the equation of state to understand my phase equilibrium, I can fully 100% develop every property in the steam tables. I can use it to calculate my specific volumes. I can use it to calculate my heats of vaporization. I can use it to calculate my enthalpies. I can use it to calculate my entropies. So the equation of state, like I said continuously, is so much more than just figuring out, what's the density of a compressed fluid. With an equation of state and ideal gas heat capacity, we literally can solve everything in thermodynamics. So let's go through and actually integrate this to give us ourselves a physical understanding of exactly what's going on. Okay, let's see, erase this stuff here. Okay. So I'm going to rewrite this expression here, but I'm going to break it up into three individual steps. We are first going to be integrating from pressure alpha, which we know is our vapor pressure. Let me write that out explicitly so you have it in your notes. P alpha is equal to the vapor pressure. And this is a function of temperature, right? Because if I change temperature, my isotherm shape is going to change, which means the pressure that satisfies these three equilibrium relationships is going to change. So for every single pressure, for every single temperature, you'll have to resolve this whole process to determine the vapor pressure. And then once you have all the vapor pressures as a function of temperature, we can figure out the heat of vaporization. Once we have the heat of vaporization, we can figure out the delta S of vaporization using the Gibbs free energy, and so on and so forth. So the first step is we're going to integrate from pressure alpha to pressure A, following along the path of VdP. Then we're going to add that to the integration going from pressure A to pressure B, again integrating the same process, plus integrating finally from pressure B to pressure alpha. And this has to be equal to 0 because this is equal to the change in the Gibbs free energy. So just to make things clear, this is going to be a negative area, right? Because the lower limit and upper limit are switched, right? P alpha is higher than PA. This is going to be a positive area, and this is going to be a negative area. And this is all going to be important when we try and put this all together. It's going to be an interesting ride for a second. All right. So when we integrate it, that's effectively the area trapped underneath the curve. So the first step, I'm going to call this step I, is going to be this area here. The next step, pressure step 2, our II, is going to be this area, going from pressure, what would we say, pressure A to pressure B, okay? So let me try and draw this. I think I have a red marker. And then the last step is going to be from pressure B, I, very faint marker, is going to be this last one here. The end result of all of this, our plot is getting very busy, so I'll rewrite it. Is that these regions here, these cancel out. So that the end result, if we rewrite the plot with the areas that cancel out as canceled out, I'll say this is area 1, this is area 2. Your vapor pressure is the line that you draw in your cubic equation of state where the area trapped in this region and the area trapped within this region cancel each other out. And this is adhering to, right, the relationship that the Gibbs free energy is related to changes in pressure and changes in temperature. When we integrate that expression, we know that the Gibbs free energy has to be constant across the phase transition, meaning delta G is equal to 0. So when we actually integrate this cubic equation of state, we did so graphically here that it just so happens to work out that these cancel. Now, normally I like to go through this arithmetic, but we're out of time. Maybe it'll be a homework problem. In fact, that's a great idea. It should be a homework problem. We can also write that, so what we did is we said that the change in Gibbs free energy is equal to 0, which is equal to the transition from the liquid, from the vapor to the liquid. So final minus initial, which is integrating from the liquid state to the vapor state. Remember, liquid state is the collection of the temperature, pressure, phase, all the information that we need to describe it, of V dP. But we can also show with just a little bit of arithmetic and calculus that this is equal to P minus vapor pressure dV, which is the more traditional way that we like to think of this. So this is the most, I guess, visual and intuitive way that we can think about it. If we were to plot out this expression here, this last bottom one right here, where we're going to be plotting P minus the vapor pressure, that means that our equation would look something like this. And then we can just integrate with respect to the volume as opposed to with respect to the pressure. So this way we're actually integrating with respect to what we're typically used to, going to the x-axis as opposed to going to the y-axis. And it can be shown that these two expressions are perfectly fine and 100% equivalent. And this is a great way to learn and understand how we can use an equation of state to calculate phase transitions and calculate all the different properties of materials that we want. This is not going to be the way that you actually solve it in a practical sense. I mean, in a pinch on the homework assignment, this might be the most visually and intuitive way to get to get you to a solution to solving for the vapor pressure. But in terms of heavy lifting, it's not necessarily going to be the most convenient way. What is going to be the most convenient way is we're going to define a new property that we will calculate at these 2 points. And we're going to say that this property in the liquid phase is equal to the same property as in the vapor phase. And this is called what? Fugacity. Right? So instead of us having to visually think about a cubic equation of state and integrating areas and crossing it off and breaking it up into individual steps and all this other kind of mathematics that is nice for us to understand, right? The computer, if you just put it in terms of numbers, it doesn't really matter. So instead, what we're going to do on Monday next week is we're going to define this new thermodynamic variable, just like we defined enthalpy, just like we defined Gibbs, just like we defined Helmholtz, just like we defined temperature, just like we defined pressure. We're going to define a new term called fugacity. Now, fugacity is not strictly necessary to solve this problem. This is one component multi-phase. Fugacity is not needed, but it's the best time to introduce it. Fugacity is needed when we're talking about multi-component, multi-phase. And as just a really quick reminder, if I have a system of pure A, and I add in a little bit of pure component B, remember, thermodynamics is infinite. Everything we're doing is at infinite time because it's reversible, so it takes an infinite amount of time to get there. It's an infinitely sized system because we're ignoring the effect of the boundaries on the edges. So if I take one molecule of B and I put it into an infinite sea of A, what happens to my entropy? It goes to infinity. That's a discontinuity, that's a problem. The fugacity is defined to eliminate this complication. For this system here, it's not really a big issue. But for when you have a multi-component, multi-phase, when you mix two things together, you have a point of initial mixing where you have an infinite gain in entropy, which is an unpleasant discontinuity. In general, we don't like working with entropy because it's kind of an abstract concept. So we certainly don't like working with infinite entropies because that's even a more frustrating and more abstract concept. Okay, any questions before we depart for the weekend? Okay, have fun. See ya.